This is our problem 3, part A, on rotational motion. What is this problem about? At a flat circular curve, radius r, in the road, the sign says maximum speed is V max. V max is a given number. If a car is to travel at this maximum constant speed without slipping, no slipping, if this car is to travel at this maximum constant speed without slipping, what must be the coefficient of friction between the car and the road? We are looking for the coefficient of friction between the car and the road. What will we do? How to approach this problem? We will use Newton's second law to solve this problem. And since this is a circular motion, rotational motion, as always, I will solve it using polar coordinates. We will introduce unit vectors. Unit vector IR, as we always did. So IR is a long radius, always out of the circle, IR. I will introduce I theta, which will be perpendicular to IR, unit vector I theta, perpendicular to IR, in tangential direction, and we will introduce vector IZ, and IR, I theta, and IZ will follow right-hand rule, which means that if I put my fingers along IR, my fingers with me using my right hand, ironically, you see my mirrored image, so I have to use my left hand to do it correctly. So you take your right hand, you put your fingers along IR, then you bend them towards I theta, and then your thumb shows you the direction of IZ, and IZ will be out of the board. I will use this sign to show that it is out of the board. This is IZ, and this is my coordinate system. Now, I already have formulas, Newton's second law, here for R, theta, and Z components of force. So let's look at each of these formulas. What do we know? We know that this car is moving along this circular path, and circular path means that radius is constant, which means that d to r by dt squared is 0, and dr dt is 0. So our formulas look much simpler now. Do I know omega? No, I don't, but I'm giving V maximum. So either I use V maximum or I find omega, and I can easily do that because I know how my tangential component of velocity is related to omega. And we remind ourselves that VR, the radial component of velocity, is 0 because radius stays constant and dr dt is 0. So I will rewrite this FR. We already did it in our video where we wrote all formulas. I don't have space here. We will do it right here. So let's write F sub R when we apply this equation to our problem. FR is MAR, and it is equal to minus this minus, because my IR is out of circle, minus M R omega squared, or it is minus M R, and omega is V divided by R, so it is omega squared V theta squared over R squared, and we get the formula for centripetal acceleration, m minus comes from this minus from the fact that IR is out, m, and then v squared over r. That's the formula that we will be using. Now, do we have f theta? F theta, the first guy is 0 because dr dt is 0. What about alpha? Look, it is moving with maximum speed, v maximum, which is constant. So v is constant, which means that omega is constant since r is constant. Omega is constant, which means that alpha is 0. Alpha is 0, which makes f theta equal to 0. Both guys are 0, okay? All we have in this plane, in the plane of the board, is radial component of force. And this radial component of force, do we know the nature of this force? Yes, this is force of friction. And since the car is moving along this at maximum speed without slipping, but at maximum speed before slipping, force of friction is equal to mu times normal force. Force of friction is magnitude of the force of friction is equal to mu, coefficient of friction that we are looking for, times normal force. And I bring this into my FR equation. So we just figure out that the projection FR is negative, so force is towards the center, acting on the car. This is force of friction. I have to put negative in front of it because it is in the opposite direction to my positive direction of IR. So it is minus mu n, and this is equal to minus m v theta squared over r, and r is given, it is capital R. What is v theta? V theta is v maximum. So let me correct this. V theta is also given. The car is moving at v max. Well, what do we know? We know m, v maximum, r. Do we know m? No, we don't know m. Uh-oh. But we also don't know n, the normal force. So what do we do? We need to use this equation. Fz is maz. So this is view from above, top view, top view. We understand that gravity is into the board, normal force is out of the board, positive z is out, so I write normal force minus mg. This is my Fz, net z component of the force. And this is equal to 0 because there is no acceleration in the direction perpendicular to the plane of the board. So I immediately know what is my normal force. Normal force is mg. And now I plug in this normal force in my equation. Look at this, minus, minus, plus mu. Normal force is mg. It is equal to m, mass, v max, which is given, v max squared over r. We don't need mass. It cancels out. So what is mu? The coefficient of friction that we are looking for. It is v maximum squared divided by r and g, acceleration of gravity. We have unknown mu on the left, and we have all known quantities on the right. Is dimension right? Mu is dimensionless. Let's check the dimension. What is the dimension for velocity? It is meters squared per second squared. R is in meters, and then g, meters per second squared. Are we doing well? Let's see. Meter squared, second squared. Yes. So in terms of dimensions, we solved it correctly. This is mu. We found mu, the coefficient of friction between the car and the road. And keep in mind that we were thinking about this car just as some box that is following this circular track. And we found the coefficient of friction, and we know that force of friction in this case, when it is moving with constant velocity, force of friction is towards the center.